Okay, everybody, back again for our next lecture on volcanoes. I'm a terrible teacher because I told you the last video that I was going to try to make these shorter, and I went about the same amount of time. So I'm going to make a conscious effort on this one to go shorter and make this lesson more acceptable to you all. So we have volcanoes. And here in Kentucky, we don't have to have much experience with volcanoes, luckily, but they are prevalent. They are areas that also have a lot of earthquakes, but not all areas that have earthquakes also have volcanoes. Volcanoes are primarily found around subduction zones where the plates converge when we're talking about plate tectonics, so specifically to subduction zones, but occasionally you'll have some hot spots, either an oceanic hotspot in the middle of the ocean, think the Hawaiian Islands, or you might have a hot spot in the middle of a continent because there's just some weakness under the surface of the earth down deep that's allowing that magma to boil up and get up closer to the surface. Think about Yellowstone and the geysers and the activity out there. So we're going to run through these. Like I said, I'm going to try to be more quick about this on this lesson. There are going to be lessons coming up that I'm going to spend a little bit more time on. Not a lot of time, but these are kind of far away from us. We just need a basic understanding of how these work. So like earthquakes, volcanoes themselves are a hazard, but they also produce other hazards that follow them or come along with them that hurt humanity if people are living in the general areas or even a little bit further away. So back to the basics, we went over this with plate tectonics, but magma is when you have basically molten or melted rock under the surface of the earth. When it gets to the surface, we call it lava. Same material, it's just at the surface, and as soon as it becomes lava, it's going to start to cool pretty quickly. So we have different types of magma. We have basaltic, andesitic, and rhyolitic. It's all basically the same material, but the amount of silica in these three different types is what makes them different from each other. Basaltic has the least amount of silica, rhyolitic has the most amount of silica. When it has silica, it allows it to be more fluid and flow more rapidly. So when it gets to the surface, like in this picture here, and think of Hawaii, if anybody has ever been to Hawaii and seen the volcanoes out there or just seen them on TV, you know there's lava flows that flow like rivers over the surface, and they go sometimes all the way to the ocean. That is very viscous. When I say viscous, sometimes you hear about motor oil having a viscosity. That means how easily it flows at like normal room temperature. Okay, does this stuff flow easily, or is it really thick? The thicker it is, the less viscous it is. It doesn't want to flow as easily. So that's the difference in the three types of lava or magma that we see here. So again, we have our volcanoes. I mentioned hot spots. Those are sort of in the middle of a continent, and that's where you just have a weakness for some reason in the crust. They bubble up. Subduction zones, that's when the plates come together and kind of crash together. We have these off the west coast of the Pacific Northwest, specifically up around Seattle and Portland, Mount St. Helens, Mount Rainier, up in that area. And then at divergent boundaries as well. I didn't mention those earlier. Volcanoes happen there too, but almost all of these are on the bottom of an ocean. So these are underwater volcanic events that we don't necessarily observe much. I mean, our scientists obviously do, but as the general public, we don't see these hardly ever. But that's also a place where volcanoes can happen. Again, getting back to the different types of lava and or magma, basaltic is a lot hotter. You see the temperature is much hotter, and this is also a color representation. So when you see it flowing out of the ground, it's very red, it's very hot, it's very viscous, it flows. As you go to andesite is in the middle, and rhyolite is the thickest and has the highest silica content. Those are different types of volcanoes that you're going to see with those different types of viscosities of magma and or lava. Volcanic eruptions. So basically you have a magma chamber underground. Again, this might be at a subduction point. It might be a hotspot in a continent. It builds pressure. Eventually that pressure has to be released. That's why you also have a lot of earthquakes around volcanoes, because you have some minor earthquakes with release of that pressure on that rock around it. But also it has to escape at some point. So you'll see a vent form, and it will come out of that vent on the volcano. So that's basically how it works. A lot of pressure involved here. So here's a few pictures that you see. Mount St. Helens over here on the left. You've got Hawaii on the right. You can see there are two different types of eruptions. Hawaiian volcanoes tend to be more lava, just lava flows flowing over land. They're actually creating new earth or new rock as they're flowing. So the Hawaiian islands are growing. The ones that have volcanoes are actually getting bigger over time. And then you have the more violent explosions that we're going to talk about in just a second. So the landforms that you see associated with volcanoes. So typically a volcano, it can be a small landform, or it can be quite a large landform, like it's in a mountain range. You have a couple other tendencies here. You have lava domes. That's kind of when you have the peaks, the big mountain peaks with lava flows and volcanoes. And you have continental flood basalts. I'm going to mention those in just a second. So the continental flood basalts. So we learned in our previous lesson that typically the rock that makes up the Earth's crust is basalt under the oceans, but it tends to be more granite under the continents. When you have a flood basalt on land, what's happened here is, you see this area in blue. This is basically the Columbia River Basin in general. And at one time in geologic history, millions of years ago, there were a lot of active volcanoes here, and that lava came up from underneath the earth and made rock in this area here. And that rock was basalt. Typically you find that under the ocean floor, but here you find it on the continent because it was moved from under the earth to the top from volcanic activity. So that's one way we can tell there used to be a lot of volcanic activity in areas like this. When you look at the types of volcanoes, the way they're shaped, when they look like a big mountain peak or a smaller hill sometimes, these are the three types that we have. We have cinder cones, which are typically the smallest, kind of quickly forming from pressure just popping up. You have a lot of kind of explosive type ash released, and that ash starts to build up over time. You have a shield volcano, which a shield volcano is what they have in Hawaii. That comes from lava flows and not big violent explosions. And then the composite cones are the ones we typically see on land, the triangular shaped mountains that we see, that if you dug down into those, you'll see successive layers of different eruptions and different depositions of rock. So here we go back to the shield volcanoes. These are the volcanoes that we're going to typically see in Hawaii. You're going to see more gentle slopes on the sides, not the really steep angular slopes like you see on other volcanoes. And that's formed just from lava flows. This basically lava is spilling out of the top and running down the sides. Not a lot anyway of big violent explosions and gases and all that stuff. This is more of a slow burn, more of a lava flow. The composite cones, again, you see the angular slopes, very steep slopes. Typically at the top you're going to see what in our minds looks sort of like a crater, or it's been cut off, because sometimes these eruptions are so violent it actually blows the top off of these mountains. So that's not uncommon to see that feature at the top of these. And again, these eruptions are much more violent, much more gases, pyroclastic flows come out of these things, and you can see here the difference in these. So look at this chart, this diagram, And this diagram is showing the heights of these mountains. Now, it's a little deceptive because Mount Rainier is actually a really tall mountain, and Mauna Loa in Hawaii is also a very tall mountain, but it's on the top of an island. Most of it is underwater, so we don't see most of it. So to us, looking above sea level, it doesn't look like it's that tall. But if you look under the water, it's built up from the ocean floor, and the entire mountain or volcano is actually up to the height of the top of the water and then coming out of the water, creating the Hawaiian Islands. Mount Rainier, very tall mountain on land, but it is on a continent, so it's all above sea level, so it appears to be much taller to us. But you can see the different shapes, much steeper, smaller base, but steeper slopes on Mount Rainier versus Mauna Loa, which is just huge with regards to volume, because this has just been lava seeping out of the top of it, running out of the top of it. In Mauna Loa, the Hawaiian Islands is a hot spot right here in the middle of the Pacific Plate. You can see the little diagram down here. The plate is moving, but we're in the middle of a plate. We just have a weakness here in the Earth's crust. It's allowing it to get up closer to the crust and start letting this pressure release of this magma come out in the form of lava, creating the Hawaiian Islands. The Yellowstone hotspot is one. It's also a hotspot, but it's under a continent out at Yellowstone National Park area in Wyoming and Montana. And you see there's several different individual magma reserves underground here in this area. That's why we have hot springs. The pressure pushes that water out. It's very hot water that's being heated by magma under the ground. At some point in the past, we've had violent eruptions there that created that flood basalt that we saw earlier in the Columbia River Basin, and likely at some point in the future we will have eruptions there again. In your lesson, I did include one video on just on volcanoes, but also one on supervolcanoes. This would be considered a supervolcano if it erupted due to the volume of magma that is found there. Craters and calderas are very similar features, but a little bit different. When we have a crater, so when you have the volcano itself, so this is the volcano. If you look at this cross section, the tunnel, the crack, whatever you want to call it, coming up, that's called the vent, and it's allowing the magma to flow to the top, become lava, and come out. Now, typically in these types of volcanoes, again, this is more of a violent eruption, so it's going to kind of blow the top off of the mountain when it does erupt very violently, and it's going to create a big crater. So, what's created right here is the crater. Now, if you look all the way at the bottom, you'll see the difference in a crater and a caldera. So, typically, the crater is going to be a little bit smaller because that is actually created just from the magma coming up. That's the entry. Think about it, that as a big pipe. That's just the end of the pipe. So when the volcano is young geologically, you just have a crater at the top. Even when the lava subsides again, you have a crater. That's a big hole in the top of the mountain. But you see all these smaller vents going off, and it's not just one typically. There's a lot of smaller ones. Over geologic time, as this magma recedes back down into the ground, and you have weathering, you have rainfall events, precipitation, snowfall, over time you get erosion, and eventually that structure weakens and the whole thing kind of falls in at the top, and that creates what we call a caldera. So that's a much bigger crater and formed from breakdown of rock and not just the original tube or pipe where that lava came out of. So again, the hazards to humanity, we have the actual lava flows and the explosive blast and pyroclastic flows from the lava, from the eruption itself. The volcanic ash that will settle around the areas, and the formation of volcanic glass. Again, all those things are hazards either right at the site, or in the case of volcanic ash, that might travel for hundreds of miles, even thousands of miles sometimes. I remember when I was very young, Mount St. Helens erupted in Oregon. It was a pretty big deal in my childhood. That was the first like mainland lower 48 volcanic eruption in the United States in probably a generation or so, maybe a couple generations. And even here in Kentucky, we could see a little bit of ash shed along, like on your car when you came out in the morning or something, from an eruption all the way out in Oregon. So when you're closer to it, though, you're going to have a buildup of ash, maybe several feet deep if you're really close to it, and that's just going to smother everything out. It's going to smother life. It's going to smother plants. It's going to smother everything, and you might have a desolate environment for a while. When we're talking about a pyroclastic flow, that's basically think about a mudslide or mass wasting, which we're going to talk about more in the next lesson. But that is a flow of superheated gases, earth, rock that just tumbles down the side of a volcano and pretty much takes out everything in its path. And that's what you saw with Mount St. Helens. There was a swath down one side of the volcano that was just absolutely destroyed. Everything, vegetation gone, everything. And of course, we've mentioned tsunamis back in our earthquake lesson. Those can also be triggered by earthquakes, especially underwater earthquakes. Or sometimes when you have a tremendous volcano, like the Hawaiian Islands are not going to create a tsunami because they're more of a gentle lava flow type, like I mentioned. But some islands are not. Some islands have the more aggressive volcanic eruptions. And when you have those on an island, sometimes, like I mentioned about Mount St. Helens, the whole side of the volcano might collapse. And if that collapses into the coast of an island, into the ocean, then that could create the beginning of a tsunami that will go across that ocean and hit whatever the closest land is. So that's how a volcano could potentially create a tsunami as well. And again, here's some diagrams of some of the things that I just mentioned to you. These are found in your textbook. This is Mount St. Helens that I mentioned before. It had a magma chamber down here that erupted out of not the top, but it had to vent to the side of the mountain. And when it erupted, it was very violent and just took the whole side of that mountain completely out. Ran all the way down to where it eventually reached flat ground. This is a comparison chart. This is in your textbook of some of the major eruptions in somewhat recent history. You see the Mount St. Helens. This is a very much prehistoric to Native American, or to America anyway, before we had settled America. You had a pretty big eruption though with Mount St. Helens, but if you go down the list, this is the one I was referencing that we experienced in 1982, I think it was the big one, and we got some of that ash here in Kentucky. Again, mass wasting, you have some of the debris flows that flow down the side. We're going to talk about mass wasting more in the next chapter, so I'm not going to talk about that a whole lot right now. But you can see this is similar to what I was talking about with Mount St. Helens. You have an eruption happening. It blew out the side of the mountain and pretty much just created a pyroclastic flow that just wiped out everything down the side of the mountain. Currently, Seattle, Tacoma, out on the west coast and Pacific Northwest are under extreme risk from Mount Rainier. If an event happened there, it is very much a likelihood that it would be toward the Seattle area. And here you can see a picture that I've visited this area several times. It's beautiful out there, but you can see this mountain all the way from pretty much Seattle. So it's well within the range of being in danger from that. And here is a diagram of the Pacific West, or the West Coast, Northern California up to the Pacific Northwest. And here's the number of times that we know that each of these have erupted in the past. So again, this is in your textbook. As far as predicting volcanoes, again, it's better than it used to be. We can't definitely predict these. I do think we have a little bit better prediction ability on volcanoes than we do on earthquakes, just because volcanoes tend to have more activity before they actually erupt. You can look at the geologic history, but you also see a lot of changes in mountains before they start to erupt. They actually bulge out on the sides. You can physically see that happening. You start to see a lot more seismic activity, more small earthquakes, and you can also actually measure the magma and where it is underground. You can actually detect it moving using some of our technology that we use to refract underground. Predicting eruptions, again, the seismic activity, you can see this diagram just showing you where small earthquakes might occur under the volcano. And that's about it for volcanoes. We'll get into the mass wasting part more in the next lesson, but I think I am a little quicker on this video, so hopefully I can keep that up and not keep telling you I'm going to and not doing it. So thank you, and again, if you need anything, feel free to reach out, and I will be happy to help out. Thank you.